Hey all, welcome to Homeschool and welcome back to Class 11 Chemistry series. I am back with the chapter Classification of Elements and Periodic Properties. See, in my previous video, I discussed everything about atomic radii, ionic radii and isoelectronic species. Isoelectronic species is one very important concept that you have to concentrate for all competitive examinations like JEE, NEET, CET, etc. I have taught you a beautiful trick how to solve questions on isoelectronic species, right? So remember that, it gives you lot of help. And coming to today's topic, it is the most important periodic property, that is ionization enthalpy. Ionization enthalpy helps to decide the chemical behavior of an element. Oxidizing nature of element, reducing nature of element, metallic character, non-metallic character, all these chemical reactivity, chemical properties can be judged based on this ionization enthalpy. So today we will talk everything, every single aspect of ionization enthalpy in a detailed way. Watch the video till the end. Definitely all your doubts will get cleared on watching this video on ionization enthalpy. Ionization enthalpy is also called as ionization potential. Okay. See here, the word enthalpy means energy. So we can also call it as ionization energy. There are so many words, but the meaning is same. Ionization enthalpy, ionization energy, ionization potential. Three different words, but the meaning is same. Okay, so what do you mean by this ionization enthalpy? It's very simple, guys. The amount of energy required, first let me write its definition. The amount of energy required, why? To remove the outermost electron. So where are the outermost electrons present? It is present in last shell. Outermost electrons are present in outermost shell or the valence shell, right? So energy required to remove that last electron from a last shell from neutral gaseous atom in its ground state is called ionization enthalpy. See, you can't remove electron from an atom which is there in a solid state. You can't remove electron from the atom which is there in a liquid state. You can only remove electron if the atom is there in gaseous state, and it should be there in its ground state, and it must be isolated. Okay, so isolated, it has to be isolated in the sense it should be single. Okay, it shouldn't be there in combination with some other atom. Okay, if you want to remove electron, you can only remove that last electron from the atom. And if you want to remove, you require energy. And if you want to remove, the atom must be isolated. It must be single. It must be there in a gaseous state, and it should be there in a ground state, right? Only then you can remove an electron, and you can remove electron with little of energy. You need to require some amount of energy to remove that last electron. And that energy, we will call it as ionization enthalpy. Okay, so we kept on studying this concept. That is, always there are some elements that loses electron, like sodium, right? It will lose one electron. And if you take magnesium, it will lose two electrons. So why do they lose electron? It is to achieve stability. And losing, simply they can't lose electron. Some amount of energy required. You need to supply to remove that electron. Okay, to lose that electron, and that energy we will call it as ionization energy. Okay, and the unit for ionization energy is kilojoule per mole. Remember the unit, this is also very important. So usually for energy in our chemistry we use this as the unit, that is kilojoule per mole. Okay, fine. And now let us try to understand what do you mean by successive ionization enthalpies. Ionization enthalpies. See, this is very simple. Just try to observe. You have aluminium, right? So aluminium's electronic configuration, if I have to write, 1s2, 2s2, 2p6, 3s2, 3p1, right? So atomic number 13, this is the electronic configuration of aluminium. Fine. Imagine if I have to remove these 3 electrons. Okay, so on removing those 3 electrons, your aluminium gets converted as Al plus 3, right? So the last 3 electrons, see which is the last shell? Last shell is your third shell. So you can only remove the last electrons, outermost electrons from outermost shell. So if I have to remove all the 3 electrons, your Al gets converted into Al plus 3. But can you remove all the 3 electrons at a time? No, you can't remove all the 3 electrons at a time. You have to remove electron one by one. Okay, so to remove the first outermost electron, you require some energy which we call it as first ionization energy. To remove the second outermost electron, you require again some energy and we call it as second ionization enthalpy. And to remove the third outermost electron, again we require energy which we will call it as third ionization energy. So these ionization energies are called successive ionization enthalpies. Okay, so let me write that in the form of equation. Say there is an element M. Okay, and if this M, on losing one electron, this will become M plus. Okay, and you know what, after losing electrons, always atoms or elements will become as cations. They get converted into cation. M lost one electron and it got converted into M plus. And here the energy required for this step, let it be IE1. Okay, so we call this as first ionization enthalpy. First ionization enthalpy. Okay, so what is first ionization enthalpy? Energy required to remove the first outermost electron. Okay, so now M plus is there. From M plus you have removed one more electron and this M plus gets converted into M plus 2. Okay, so M plus, from this you removed one more electron, it got converted into M plus 2, and energy, actually this is second outermost electron. When you have 3 outermost electron, in the first step you removed this and in the next step you are removing one among the 2. Right, that is second outermost electron you have removed, and energy required for this step is called as IE2. Okay, so which we will call it as second ionization enthalpy. Whereas from M plus 2, if you have removed one more electron, then this M plus 2 gets converted into M plus 3. And energy required to remove the third outermost electron is called IE3, which we can call it as third ionization enthalpy. Okay, so this IE1, IE2 and IE3, they are called as successive ionization enthalpies. Okay, is the concept clear? So very, very important. So usually we have a trend here. Okay, IE3 is always greater than IE2, which is greater than IE1. So sure short direct question can be asked about the relation between IE1, IE2 and IE3. Okay, so always whenever you want to remove the inner electrons, it's difficult. You need to supply more energy because the inner electrons are more near to the nucleus. Okay, so as you go to inner electrons, they are more near to the nucleus, they have more attraction from nucleus. Okay, so when some electron is experiencing more attraction from nucleus, you can't remove that electron that easily, and to remove that, very high energy you need to supply from outside. Okay, so that is why IE3 is always greater than IE2, IE2 is greater than IE1. Okay, so one example I can show you here. See, the same aluminium I will take. Okay, so you have aluminium. I am removing one electron from aluminium. You have got aluminium plus. Okay, and energy required for this step, which we will call it as IE1. So let that IE1 is 500 kilojoule per mole. And from Al plus, you are removing one more electron, then Al plus gets converted into Al plus 2. So actually this is the second outermost electron, and this ionization energy, which we call it as IE2, and let's imagine its value is 1800 kilojoule per mole. Okay, so I am actually giving approximate values, I am not giving you exact values. Exact values are near to these values itself. Okay, and from Al plus 2, I am removing one more electron, and this Al plus 2 gets converted into Al plus 3. And let this ionization enthalpy be IE3, and what is its value? It is around 2000 kilojoule per mole. Okay, so energy required for removing first outermost electron is this much. Energy required to remove second outermost electron is this much. Energy required to remove third outermost electron is this much. You see the value, IE3 is always greater than IE2, IE2 is greater than IE1. Okay, and you know what, for this equation, Al, on losing 3 electrons, you will get Al plus 3. Okay, so for this, ionization enthalpy can be sum of all this. Okay, so 500 plus 1800, 500 plus 1800 plus 2000, if you do, you will get total ionization enthalpy. Okay, but actually, all the 3 electrons you cannot remove at a time. They have to be removed one by one in a stepwise. So first you need to remove one electron. For that you need some energy. How much? This much. To remove second electron from outermost shell, you require this much energy. And to remove third outermost electron, you require this much energy, right? So altogether, to remove 3 electrons, the energy required is this plus this plus this. Okay, so it is always removed stepwise. Right? So hope you are clear with successive ionization enthalpies. Always remember guys, third ionization enthalpy is greater than second, second is greater than first. This is really very, very important relation. Okay, so now we understood what actually we mean by ionization enthalpy and successive ionization enthalpies. Okay, we can only remove outermost electron, right? So because outermost electrons are somewhere very far from nucleus, attraction will be very less, easily you can remove that electron. Okay, so and removing is not that easy, you need to spend some energy. That energy itself we meant by ionization enthalpy. Now let us discuss about factors affecting ionization enthalpy. There are various factors on which our ionization enthalpy depends. Let us discuss them one by one. See guys, there are mainly 5 factors that affect ionization enthalpy. That means our ionization enthalpy depends majorly on 5 factors. Under that, the first and very important factor is atomic size. So in my previous video, I discussed everything about atomic size, isn't it? So usually as the atomic size increases, okay, so remember this is really very important. As atomic size increases, what happens for our ionization enthalpy is it decreases. Okay, so always our ionization enthalpy is inversely proportional to atomic size. So this is really very important. So why? See, observe carefully guys. This is a smaller atom. You have only 2 shells. Electrons, valence electrons are there in the second shell. And you have one bigger atom. There are so many shells. Okay, so this is where your valence electron is there. Okay, so this is your nucleus. In both atoms, this is nucleus. This is shell number 1, this is shell number 2. And here 1, 2, 3, 4, 5. This is your shell number 5. Okay, say in which case attraction between nucleus and electron is minimum. You see here, electron is in second shell. Second shell is much near to the nucleus. So in this case, what you will observe is attraction between nucleus and last electron is more, isn't it? Since attraction is more, what happens? You cannot remove this electron easily. And to remove that electron which is in greater attraction with nucleus, you need to spend high energy. You need to struggle to remove this electron, because electron doesn't come easily, because electron is more attracted towards nucleus. Nucleus is holding the electron very tightly. Okay, so it's not easy to remove this electron. Okay, you need to spend more energy. So in this case, more ionization energy. After all, what do you mean by ionization energy? Energy to remove this last electron, right? So it's not easy to remove this electron because of high attraction. Okay, whereas you see electron is somewhere very far. So as the distance between the nucleus and last electron increases, you know what? In this case, you will observe less attraction. Okay, so this electron is not too much attracted towards nucleus. Nucleus is not holding this electron that much tightly. So it's very easy. This electron can come easily. So when it is easy to remove, why do you need to struggle? With very little energy, you can remove this electron, right? So in this case, less IE you will observe, right? So more size, less ionization enthalpy. Less atomic size, as the size less, you would observe more ionization enthalpy. Okay, so this is how our ionization enthalpy is always inversely proportional to atomic size. Okay, so now let us discuss about the second factor, nuclear charge. So first, try to understand what do you mean by nuclear charge. Nuclear charge means total positive charge of nucleus. So who is responsible for positive charge of nucleus? It is protons. Okay, proton is responsible. Say for example, this is one atom. Okay, so where electron is there? Electron is there in the second shell. This is another atom. This is a nucleus. Another atom where electron is there in a second shell only. Okay, two different atoms. Okay, imagine here you have 2 electrons and here you have around 4 electrons. Okay, say let me take this is our, what do we say, 2 electrons in the last shell. We can say this as, beryllium. Okay, let me call this as carbon. Okay, so beryllium's electronic configuration 1s2, 2s2. In the second shell, you have 2 electrons. And carbon's electronic configuration 1s2, 2s2, 2p2. Right? So, second shell has 4 electrons. Fine. Can you tell me in which case nucleus is more positive? See here, how many protons are there inside the nucleus of beryllium? It is 4 protons, atomic number 4, right? 4 electrons and 4 protons would be there. Whereas in carbon, how many protons are there inside the nucleus? 6 protons, right? So, you see, more positive charge you will observe in case of carbon. Okay, so as the positivity of nucleus increases, what happens? Attraction between the nucleus and outermost electron increases. So here you will observe more attraction. Okay, so more the nuclear charge, say nucleus has become so much strong, so much positive, so that what happens? It will try to pull all the outermost electrons tightly towards itself, so that if you want to remove any of the electron, it's highly difficult. You need to spend very high energy. Right? So that is the concept here. As the nuclear charge increases, what will happen for ionization energy? Ionization energy also increases because of more attraction between nucleus and outermost electron. Okay, so here what I can write here is ionization enthalpy is directly proportional to nuclear charge. So what do you mean by this? As nuclear charge increases, our ionization enthalpy also increases. Right? So these are 2 simple factors which can affect ionization enthalpy. Let's discuss about the third factor, shielding effect or screening effect of inner electrons. This is really very, very important, guys. Try to understand carefully. In a common language, I can say that screening effect is nothing but fighting between outermost electrons and inner electrons. Okay, because of this fighting, you know what? Outermost electrons will not get nice attraction from nucleus. See guys, suppose if this is your nucleus and imagine this is your first shell which is completely filled with 2 electrons, and this is your second shell completely filled with how many electrons? 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And this is your third shell filled with 2 electrons only. So which is your outermost shell? Our outermost shell is the third shell. So this is your outermost shell or valence shell, and these electrons are your valence electrons. Okay, see, the attraction between nucleus and these electrons decreases. One is this shell is far away. The other reason is due to screening effect. It's because there are some electrons. See, electrons which are there in a second shell and electrons which are there in a first shell. These electrons, we will call it as inner electrons. What do we call them as? Inner electrons. Electrons which are there in inner shells is called inner electrons. So these inner electrons will act as a barrier. Okay, they will act as a screen. There is always a kind of repulsion between inner electrons and outer electrons. Okay, say for example, this is a parent. Okay, and this is you, and these are your younger siblings, that is your brothers and sisters, small brothers and sisters. Okay, so what happens is always the small brothers and sisters are jealous, right? So they want more attraction from parent. The same logic you can apply here. So these your inner small brothers and sisters are not allowing outermost electrons to get attraction from nucleus. They are acting as a barrier. So here your siblings are always barriers between you and your parents. Okay, because your parent, since they are very small, your parent concentrates only on smaller ones. They focus more on smaller one, they pamper more on smaller ones, right? So here actually your siblings are not allowing you to get enough attraction from your parent, right? So the same concept here. They always are fighting. We always fight with our siblings, with our brothers and sisters, isn't it? So you know what, the same thing, electron, both negative charge, so you would observe more repulsion, and these fellows, these inner electrons will not allow outer electron to get attraction from nucleus. That is what we mean by screening effect or shielding effect. Let me write it here. Inner electrons do not allow outer electrons, outer means valence electrons, outer electrons to get attraction from nucleus, right? So when outer electrons are not getting nice attraction from nucleus, they can be removed easily. So these guys can be removed easily. Removed easily means what? You no need to struggle too much. With less ionization enthalpy, you can remove these electrons easily. Okay, so what I can say here is more the screening effect, okay, screening effect, less is the ionization enthalpy. Less is ionization enthalpy. I can say, in other words, ionization enthalpy is inversely proportional to screening effect. Okay, so when you have more and more inner electrons, the outermost electrons do not get much attraction from nucleus, right? So when you have more and more inner electrons, they screen more, they act as a strong barrier, right? So more the inner electrons, more is the repulsion, and lesser is the attraction between electrons, outer electrons and nucleus. So you know what? Less ionization enthalpy. Okay, so more ionization enthalpy is always inversely proportional to screening effect. More the screening effect, lesser will be the ionization enthalpy. Okay, so this is how our ionization enthalpy also depends on screening effect. Guys, also remember a point that if the electrons, inner electrons, if they are there in s orbital, those electrons will act as a better screeners. They are like much younger brothers and sisters, and they always want parent to attract towards them. They want complete attention of parents towards them, right? Much younger brothers, if they are 2-year-old 3-year-old kids, they expect more attention from a parent towards them. So it's like the electrons which are present in inner s orbitals are better screeners. Okay, so they act as a better barrier between you and nucleus, right? So screening effect is more for electrons present in s orbital than p greater than d greater than f. Okay, so screening effect of s electrons, inner s orbital electrons is greater than the electrons present in p orbital than the electrons present in d orbital. So electrons present in f orbital is poor screeners. Okay, so they are like, they are very much careless. Okay, they actually allow you guys to get attraction from nucleus. Okay, so they are actually very nice siblings. They even want you also to get attraction from the parent. So actually, who is a bad sibling? The bad sibling is the electron present in a s orbital, because they are much younger. They want complete focus towards them. Okay, so these guys are very, very bad. But the electrons present in p, okay. Electrons present in d, much okay. electrons present in F, I can say they are friendly with you. Okay, so even they allow you to get attraction from nucleus. Okay, so they also screen, but the way they screen is much lesser than the way you are screened by, S electrons. Okay, so that's all about screening effect or shielding effect. Now let us go for the fourth factor, penetrating power of electrons. See, under penetrating effect of electrons, you will learn the difficulty of removal of electron in different orbitals. Say we have electrons in s orbital, p orbital, d orbital and f orbital. Electrons of f orbitals is easier to remove, whereas electrons present in s orbitals is always difficult to remove, because s orbital is always near to the nucleus. Okay, so here electron in s orbital is difficult. It's very difficult to remove. Okay, because you know what, s orbital is very much near to the nucleus. Okay, so usually electrons of s orbital is difficult to remove than p orbital, d orbital and f orbital. So here, if you want to remove any electron from s orbital, you require high ionization enthalpy. Okay, so whereas if you want to remove electron from f orbital, actually less ionization enthalpy is required. Okay, so why it is very difficult to remove electron from s orbital? If the outermost orbital is s orbital, if last electron is present in s orbital, then I'm talking about. Okay, so that is the situation where I'm talking about. So if an electron is there in s orbital, it's always very, very difficult to remove. Okay, for example, you see our helium is there. What is its electronic configuration? 1s2. See, our outermost electron is there in s orbital. It's very difficult to remove. Okay, it's very difficult to remove this electron from helium because the last electron is in s orbital. So if you want to remove this electron, you need to spend very high energy. So I use very high ionization enthalpy to remove such electron. Okay, so like this, it's very difficult to remove electron in s orbital than electron in p orbital, and this is the order. Okay, so it's very compared to sp, it's very easy to remove electron from f orbital because f orbital is not very much near to the nucleus. Okay, it is somewhere hidden. Okay, so that's why it's very easy to remove electron from f orbital. So this is our fourth factor. Now let us go for the fifth factor, that is electronic configuration. See guys, we can also decide whether we need to supply more energy or less energy to remove an electron based on electronic configuration. Okay, so usually the elements with stable electronic configuration have very high ionization enthalpies. So when do you call electronic configuration as stable? If you have fully filled shells or half filled outermost shell. Okay, so if outermost shells are fully filled or half filled, okay, then we say that particular electronic configuration is stable. Okay, so for example, you take nitrogen. If you write electronic configuration of nitrogen, atomic number 7, 1s2, 2s2, 2p3. You see here, p orbital is half filled. P orbital is half filled, right? So definitely I can say that this is stable electronic configuration. Okay, and then you observe neon where atomic number is 10. If you write its electronic configuration 1s2, 2s2, 2p6. See, s orbital is completely filled, p orbital. The entire shell itself is completely filled with 8 electrons. So this is the fully filled condition, we say. Fully filled condition. So this condition is also considered as stable condition. So if an element shows half-filled orbitals or fully filled orbitals, then we say that particular electronic configuration is very, very stable. If electronic configuration is stable, then in that case you cannot remove these electrons that easily. So very, very high ionization energy you have to supply. Okay, so it's not easy to remove outermost electron of nitrogen because it has stable electronic configuration. Okay, if you want to remove this outermost electron, you need to supply more and more energy, right? So what I want to summarize is, if any element has stable electronic configuration, it's not easy to remove outermost electron in that condition. So you will always expect more ionization enthalpy. Okay, so if electronic configuration is stable, then more ionization enthalpy, right? So these are the 5 factors you have to keep in mind before deciding about ionization enthalpy of elements or atoms. Okay, so now let us discuss about variation of ionization enthalpy in a period and in a group. When you go from left to right in a period, what happens for ionization enthalpy? Will it increase or decrease? And what happens for our ionization enthalpy when we go from top to bottom in a group? All that we will discuss. First point, variation of ionization enthalpy across a period. Across a period in the sense what? When you go from left to right in a periodic table. Okay, so RIGHT, right? Okay, that means let me take second period elements. You have lithium, beryllium, here boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, so usually when I go from left to right, can you tell me what will happen for the size? Size will always decrease. So if size decreases, what happens for ionization enthalpy? You can always decide based on the size. Size decreases, our ionization enthalpy increases. Yes or no? Lesser the size of an atom, smaller the atom, outermost electrons are more attracted towards the nucleus. It's very difficult to remove that electron. So more energy you have to supply. Right? So smaller the atom, more is the ionization enthalpy. So what happens? Ionization enthalpy increases. It increases from left to right. Okay, so this is really very, very important. But there are exceptions always. Okay, so the exception is, you know what? This is your second group element, right? And this is your 13th group element. Okay, let me write it here. Beryllium, boron, separately I'll write. Beryllium's electronic configuration 1s2, 2s2. Whereas here 1s2, 2s2, 2p1. You see, in which case electronic configuration is stable. So here you have stable electronic configuration. Here electronic configuration is not stable. Okay, size wise, if you see, this guy has lesser size, so this must have more ionization enthalpy. Okay, but since electronic configuration is stable for second group elements, your beryllium has more ionization enthalpy than boron. I can say that your second group elements have more ionization enthalpy than 13th group elements. So usually 13th group elements size is small, no, compared to this. These guys must have more ionization enthalpy, but this is an exception. So similar exception you will find in 15th group and 16th group elements also. So nitrogen's electronic configuration 1s2, 2s2, 2p3. Oxygen's 1s2, 2s2, 2p4. So this is a stable electronic configuration. This is unstable electronic configuration. So always nitrogen has more ionization enthalpy than oxygen. Usually normal trend is what? Ionization enthalpy must increase as you go from one group to another to another. So as a normal trend, you will expect that 16th group elements will have more ionization enthalpy than 15th group elements. But no, since 15th group elements have stable electronic configuration, these guys have more ionization enthalpy, okay, than oxygen. Okay, so these are exceptions, guys. Always beryllium has more ionization enthalpy than boron, nitrogen has more ionization enthalpy than oxygen. Not only this, I'm talking about the entire groups. Okay, so this is one exceptions you need to consider. So they can be asked for competitive examinations in various formats. You must be familiar with the concept. Okay, fine. So now the next point is variation of ionization energy down the group. Okay, so usually let me consider the first group elements: hydrogen, lithium, sodium, potassium, rubidium, cesium. So as you go from top to bottom, what will happen for size? Size will increase. So if size increases, what will happen for ionization enthalpy? Ionization enthalpy decreases. Okay, so cesium has the least ionization enthalpy than any other element in the periodic table. Remember, cesium has the least ionization enthalpy. Least ionization enthalpy. Okay, because cesium is larger in size. More the size, the last electrons are located somewhere very far. They will not get more attraction from nucleus. So it is very much easy to remove such electrons. Okay, so remember guys, cesium has the least ionization energy than any other elements in the periodic table. And what about our noble gases? So usually noble gases have maximum ionization energy. So maximum ionization energy you will observe with noble gases because they are all very stable. Okay, so they have that 8 electrons in the last shell and they don't want to lose electron. So if you want to remove electron from noble gas, it is very difficult. So you will observe maximum ionization energy for noble gases. Okay, so this is how the variation of ionization energy across a period and variation down the group. Okay, so that's all about ionization energy, guys. I have covered all the points here. And group wise generally we say it is decreasing, but here and there some exceptions you will find something like this. Okay, but all of them you will study when you study group wise chemistry. We study first group elements, second group elements. So group wise chemistry, when you study, you will see what exceptions are there in a normal trend. Normal trend is from top to bottom ionization enthalpy decreases. That means compared to hydrogen, lithium has less ionization enthalpy. Compared to lithium, sodium has less. Compared to sodium, potassium has less, like that, decreasing order. But there are some exceptions here, like we discussed exceptions here across a period. Okay, but you will learn those exceptions when you learn group wise chemistry. Okay, so with this I am completing this concept, ionization enthalpy. Hope you enjoyed the concept and got all your doubts clear. So post your opinion in the comments. Let me know how far you understood a concept. Okay, so in my next class, I will come up with one more interesting periodic property, electron gain enthalpy, which we can also call it as electron affinity. Okay, so till then, revise the concept, take care, do subscribe our channel to learn the concepts in a easiest way. Thank you.